So far in this chapter, I have very directly stated that the divergence of f is calculated by doing the dot product of nabla with f, and that the curl of f is calculated by doing the vector product or the cross product of nabla with vector f. But this expression seems to come from up above in the heavens, right, or something. I didn't justify it. So it's quite surprising that such a simple definition leads to some concept that is so clear and physical, such as the curl, which relates to the rotation of the field, or the divergence, which rotates to the fact that the field is born or dies at a certain point, right? So I guess that the point in this video is to give you the actual real definition of the divergence, from which you can derive how to calculate it. Okay? So I'm going to give you only the definition. The way of how to calculate from the definition, how to calculate the way of this expression here, this is left for the additional chapter 5.2, which I said was optional. It's not included in the exam, but if you are interested in knowing it, it's there. Also, I will show you a picture of how that derivation looks. But for now, let me just tell you about the definition of the divergence of f. So you have a vector field f, which looks like something, yeah? And now we want to calculate the divergence at some point. So what you do is you create, for example, I want to calculate the divergence here. So the way to calculate the divergence is you imagine a volume that surrounds this point, and this is a closed volume, okay? And this closed volume is associated to a closed surface that surrounds this volume, right? So this is like this shape that surrounds the volume. So now the divergence of f is defined as, so this is a definition, okay? This is the starting point. So it's defined as the limit when the volume goes to 0 of what? Of the flux of the field outside of this volume. And you remember that flux is written like this, flux of f dot ds in the surface S. So the surface S encloses the volume B. So we do the flux of the field on the surface S, and we divide it by the actual volume B. And we do that in the limit when the volume goes to 0. So we consider a smaller and smaller volume, and we calculate the flux outside of that volume and divide it by the volume. Okay? And in this way is how the way you can imagine it is that you imagine a differential of volume around the point, and you calculate the flux into this, out of this differential of volume, and then divide by dv to get the divergence. Okay? So using this definition, you can derive the equation nabla.f, and although I'm not going to do it, here is a spoiler. If you are interested, go into the further notes, which is chapter 5.2. So it's this hidden chapter I told you about, which is available in kits. If you go to the topic corresponding to vector calculus, you will have an optional section with a PDF named Further Vector Calculus, and in there I describe this derivation, but it's actually fairly simple. It's just that you want to calculate the divergence at some point, so you imagine a differential volume with sides differential of x times differential of y times differential of z, and basically you find the vector field f at each of these sides, and they will be given by a first order Taylor expansion, and then you calculate the flux by multiplying the area times the field, as you know. Yeah, so you do that for the 6 phases and you add them up, and the total flux outside of this differential volume, when you divide it by the dv, which will be dx dy dz, you end up with nabla.f. Okay? So if you're interested, please go and see the derivation in the optional notes. Then the curl of f, I will give you I will leave that for the next video.